Great. I want to join Pete in welcoming everybody here, and also thank Pete and Hacker Labs for helping organize this. Really excited by the turnout. This is more than we could have expected, and also by the great guest speakers who you'll be hearing from in addition to me. I have to go through the obligatory recruiting pitch. You guys may have already seen makeshift recruiting booth near the front. We have some great recruiting people here: Alex, Tracy, Jeff, Christina, all ready to talk to you if you have questions. So please make use of them. Basically, anybody in a Lyft T-shirt will point you in the right direction if you're lost or looking for the right person to talk to. So I'm going to make this pretty quick and painless. Hopefully, I want this one slide to essentially do the selling for me. Hopefully. And so I've just assembled a few interesting pictures of data science visualizations that have come out of a handful of the projects that we're working on here. And these are only the ones that sort of lend themselves to these nice pictures. We work on a number of different things, but some of the things you see represented here are supply and demand balancing, travel time estimation, fraud classification, location estimation, and a number of other things. Yes? Sure, will do. Thanks for the heads up. So as I said, these are just some of the exciting problems we work on. I think that this slide should speak for itself in the sense that I challenge you to find a company of our size who has as diverse a set of data science problems to work on a day-to-day basis. I think we take the cake in that department, so that's what really drives the data scientists we have working here. And to handle this diverse set of problems, we need a diverse set of people. So we have data scientists from many different academic backgrounds, including optimization and operations research, mathematics and statistics, engineering, physics, you name it. Transportation science is another big one. So really excited to keep growing the team and to have all of you talk in more depth about these problems. Unfortunately, I can't go into much detail about these problems tonight. I'll be talking about something which I hope is just as interesting. But if you are dying to talk about any of the data science problems we have here, you're more than welcome to come back on another day, have lunch with us, or stay the whole day if you like, 5 hours or so, and talk to a bunch of people about all the nitty-gritty details of these problems. OK, so what will I talk about? We've tried to organize a theme around experimentation for two reasons. One of them is that it's something we can talk about somewhat freely without giving away too many secrets. But I also think it's a very important topic, and one which is sort of given short shrift sometimes in the data science community. So this quote is meant to be somewhat amusing. It's a quote from Fisher that I've sort of modified to fit the times a little better. So I'll leave it up for your amusement. But the main point I'm trying to make here is that I think we tend to treat experimentation and A/B testing as sort of a solved problem in the tech community. And I think that's a potentially dangerous mistake. And so I'm hoping that one thing you'll get out of the talks tonight is a sense for what some of the pitfalls are and some of the things we need to watch out for, and some of the opportunities that we have as data scientists to make big contributions to make experimentation as rigorous and as efficient as it can be. OK, so the particular area I'd like to sort of dig into a little bit more is what's technically known in statistics as interference. And this is something which plagues experimentation in sort of a marketplace setting like what we have here at Lyft. OK, so here's a quick outline. I'll give you a very simple example, which I hope will kind of motivate the problem. I'll talk about what this interference thing actually is. I'll tell you how we can use simulation to sort of get a handle on how big of a problem it is. And then I'll try to propose some ideas for how to fix it. OK, so here is pretty much the simplest example that I could come up with. It imagines a sort of an imaginary Lyft universe where we only have 2 passengers and 1 driver. Unfortunately, we're in an undersupply situation. That is to say, we don't have enough drivers to satisfy all the demand in this particular example. And the sort of treatment that I want to think about in the example and later on in some of the other things in the talk is what would happen if we were to subsidize prime time. So as many of you know, when we're in these undersupply situations, we sometimes have to raise prices. That's called prime time pricing. Let's think of it as just a binary thing for this example. And so what would happen if Lyft paid prime time, and so the user did not have to worry about paying this extra cost? So that's the scenario I want to sort of talk about. So as in any experiment, we would have a control situation and a treatment situation. So the control group would be those who had who received prime time, as they normally would. And so we have to sort of have a model for how those people would behave. And so the model I'm going to propose is that imagine those people, given that they open the app and see prime time, they're going to take a ride with probability 1/2. So 50% chance they take a ride, 50% chance they say, no, this is too expensive, I'm going to use another option. OK, so that's the control group. The treatment group would be those for whom we paid the prime time. And let's just assume for simplicity that those users would take a ride all the time. 100% of the time, they open up the app and see no prime time, they're taking a ride. OK, so that's the basic setup. And let's assume that we have these two users, A and B. They're equally likely to open the app first. They'll probably open the app within a few seconds of each other, so very close in time. All right, so this is the cartoon. OK, so in any experiment, there's usually a metric that we're interested in measuring. So in this case, let's imagine it's the total rides that happen on the Lyft platform. And so what we want to estimate is sort of like in these two counterfactual universes, one in which everybody got prime time and the other in which nobody got prime time, what would the effect on the total rides we served be? In other words, what would the difference in expectation, if you will, be between the number of rides served in these two sort of parallel universes? Unfortunately, we can't observe both of those parallel universes, and that's where sort of the purpose of experimentation comes in. But we can, in this case, since we have this model, we can say exactly, on average, what would happen in the two scenarios. And if you do a little bit of simple probability and arithmetic, what you see is that in the global control setting, so that's all the sort of pinkish box on the bottom left, where everybody gets prime time in this undersupply situation, the total number of rides you would expect is 3/4, so slightly less than one ride on average. The reason for that is pretty simple. Either the first person to open the app takes the driver, and that happens with probability 1/2, or the first user chooses not to take a ride, and then the second user takes a ride, also with probability 1/2. And so you end up with 3/4. So the blue box on the lower right, that's the global treatment scenario. And in that scenario, it's much simpler. Nobody has prime time. The first user who opens the app is guaranteed to take a ride, and that's the end of the story. Second user is out of luck. And in that situation, we expect one ride, and we'll always actually get one ride. So then if you compute an average treatment effect between those two different configurations, so this is the thing that in the ideal world our experiment would estimate perfectly, you see that by subsidizing prime time in our treatment, we've managed to increase the expected number of rides by 33%. So that is sort of the ground truth metric we're after here. OK, so now what would happen if we just used a traditional naive A/B testing kind of framework and said, let's randomize half of our users to the treatment, half of our users to the control, and measure differences between those two groups? So in this situation, let's assume that means that passenger A is assigned to the control, gets prime time. Passenger B is assigned to the treatment, and so we subsidize prime time for passenger B. OK, so you have to go through a little bit more arithmetic and probability. And this is sort of what pops out. For the control user, user A, they get prime time, and there's a 50% chance they open the app first, 50% chance they open the app second. So the only way for them to get a ride, because B will just steal the driver, is to both open the app first and also choose to convert. And so it works out to a 1/4 of an expected ride for passenger A. In comparison, for passenger B, the passenger who doesn't have prime time, again, two things can happen. That user can either open the app first or second. If passenger B opens the app first, she'll always convert. She'll get the ride. And if passenger B opens the app second, she has a 50% chance of still having a driver available and therefore getting a ride. And so you get 3/4 of a ride on average for passenger B. OK, so what happens if you take a difference between those two numbers? In relative terms, you get an estimated treatment effect of 200%. So now it looks like the treatment of subsidizing prime time increases rides by 200% on average per user. Obviously, this is wrong and is very different from the metric we're after, which we said was 33%. OK, so the question is, what happened? And my claim is that this is a very elementary example of what we'll call interference, and we'll talk about it in more detail. But in sort of simple terms, in intuitive terms, what happened is that the treatment that passenger A got, that is the fact that they got prime time, actually helped on the network level, helped the overall sort of ecosystem by helping to balance the supply and demand ratio. So because user A saw prime time, driver D had a higher probability of sort of sticking around longer and being available for the next passenger. So in this case, even though passenger B was treated with no prime time, that passenger got the benefit, accrued some of the benefit that the prime time that A got sort of generated for the system as a whole. So in other words, A's prime time was kind of like protective, if you will, to sort of passenger B's ability to take a ride successfully. OK, so here's a little bit of more technical detail on interference. If this is too technical, don't worry too much about it. But to talk about it sort of in more accurate terms, you need to think a little bit about causal inference and a mechanism in causal inference, which is potential outcomes. So in causal inference, you typically imagine that every unit, every user in this case, or other experimental unit, has two possible outcomes, one which would happen under the treatment and one which would happen under the control. And we only observe any one of those two potential outcomes for any particular unit. But we can imagine that the true thing we want to estimate would correspond to the difference between those two things. So here Z is a binary indicator that a unit received a treatment. And so what is this notion of interference? In the third bullet, there's a definition, and it's quite a simple one. It just says that the potential outcomes, these two values for a given user or a given unit I, actually depends on the treatments that the other units received. So here Z minus I is notation for the sort of treatment assigned to the other units. So in the example we saw, the fact that passenger A got a particular treatment affected the outcome of passenger B. And this leads, as we saw, to estimators which are quite biased and can be quite different from what we're actually trying to estimate. So where this sort of originated in the literature was in medical statistics. And they found that for vaccinations, for example, this was a problem. So if they did a study where a brother and sister, one of them was assigned a vaccination and one of them was assigned like a placebo, they found that the vaccination benefit somewhat accrued to the person who got the placebo. Because if your sister is less likely to get the flu, then you're also less likely to get the flu, and so on. So a very kind of analogous situation to what we saw in the primetime example. OK, so here are some papers on this. You can look at these at your leisure. I think only the third one is kind of interesting, and I'll get into it in more detail later. OK, so here is just a brief snapshot of sort of what are some experimental designs that we can use at Lyft, or that sort of immediately come to mind if you're thinking about the kinds of experiments that Lyft and similar companies would like to do. So the first one is what we already discussed, which is just basic A/B testing on users, so like randomized passengers or drivers, or users generally, to different treatment groups. And what we saw in that case was that we had a situation of interference, even in a very simple example, which caused some bias. OK, but the good thing about these user A/B tests is that if we have a lot of users, which hopefully we do, we have a small variance, and we can estimate that variance very easily by doing some simple resampling, for example, to get those variance estimates. So that's good. So the A/B testing that people typically do is sort of on the bias but low variance end of the spectrum. Sort of in between, there's a notion of spatial randomization. So since Lyft operates on a sort of a network, on a map, literally on a map, it seems reasonable that we can subdivide space, like a city or a region, into a bunch of different spatial units and then randomize those to different treatments. So I say that's somewhat intermediate because, as we'll see, that has a bit more variance than the sort of user A/B test, but it has less of a bias issue. And furthermore, we can estimate the variance pretty easily using some of the same resampling ideas that you would use for user randomization. The third bullet here is a type of design which I think is somewhat unique to Lyft or companies like Lyft, and that is the notion of randomizing time intervals. So the idea here is you take a block of time and you treat the entire network with one particular experiment variant for that block of time. And then the next block of time, you swap to the other variant. Assuming there's only two, you go from treatment to control or vice versa. And then you keep alternating back and forth between treatment and control for successive time intervals until you run it long enough. And then you can aggregate data from like treatment intervals together and try to get some sense of the experimental effect that way. So we've used these kinds of things to good effect, I would say, at Lyft. The great thing about these is they don't suffer from the network interference problem, because at any given time, modulo some edge effects or some boundary effects, all the users are getting, the entire network is getting the same treatment. But you do have to discard some data at the boundaries of these blocks. And the variance in these experiments tends to be quite large. And the reason intuitively is that blocks of time can be very different. So it may rain for 15 minutes in a day, and that affects Lyft's business quite a bit. There may be like a ball game that gets out in one particular block of time, and that affects things. And so you end up with a lot of outliers and just a lot of variance. And probably just as troubling as the size of the variance is the fact that there's no real rigorous way that I know of, at least, to estimate this variance in a meaningful way. And so that makes it very hard to get a handle on the various metrics you're trying to estimate. OK, so how can we sort of quantify this sort of bias-variance trade-off that I showed in the last slide? So we have a really great simulation framework here at Lyft. This was built sort of jointly by the different data teams at Lyft. Some of you who attended the Data Eng conference that Pete spoke about may have seen Saurabh, a member of our data platform team, go into a lot of detail on the simulator. I won't go into much detail except to say that it was an early win for Lyft data science, something we're really proud of and we make tremendous use of. And allows us to test huge numbers of algorithmic changes without necessarily running live experiments, but getting a sense for how they'll perform. It's backed up with predictive models of user behavior and all sorts of fun stuff. Uses production code, highly parallelized on EC2 and so on. But the goal of this particular experiment was to take that toy example I showed you and actually run like a larger scale version of that on actual Lyft historical data, but do the same basic treatment, that is subsidized prime time for some subset of users. And so the three designs I chose, the three experimental designs I chose to simulate, were firstly the sort of alternating time interval design that I mentioned, using hour blocks for simplicity. And the second and third were two different types of spatial randomization. So basically where I divided cities into grids and used either sort of a coarse or fine grid in order to choose units for randomization. So those are the three different flavors I simulated. I did 50% treatment groups, and also simulated the sort of global treatment and control, which would give me the estimand, in some sense, the true ground truth metric that we wish to estimate. OK, so here are some brief results. So I actually looked at two rides. So in addition to two metrics, that is. In addition to the rides metric that I discussed in the toy example, I also looked at something that's much more of a network level metric, and that is ETA. So for those of you who use Lyft, you'll be familiar with that term, but it's simply the average pickup time that a user can expect when they open the app and that they see displayed in the app. So the story for these two metrics is somewhat different. So let me talk through these plots a little bit. The x-axis here is the ground truth. So this is what I got by running the global treatment and the global control, comparing them. So this is like the x-axis is what we're trying to estimate. The y-axis is what we actually estimated in each of these experimental designs. So ideally, things would lie on that diagonal gray y equals x line if everything was working perfectly. The different colors correspond to the three different designs I mentioned. So the purple is the time interval design, pink is a fine spatial grid, and green is a coarse spatial grid. And the shapes correspond to two different markets that I ran this in. That's somewhat less important. OK, so starting first on the left-hand side, you can look at for the rides metric, things are pretty well behaved. An increase in ETAs that we observe when we subsidize prime time in this way. OK, so this slide summarizes basically the same information in a bit more of a compact way. So here I'm just looking at mean square error and saying like which design gives the best mean squared error, the smallest mean squared error in these two metrics. And you can see that, again, there's a sort of a double story here. So for the rides metric, it looks like the spatial designs perform super well and give lower root mean squared error than the time interval-based approach. And for ETAs, it's sort of dramatically the opposite. So as you can see, the fact that the time interval-based estimates were kind of highly variable in the sense that there were those separated point clusters doesn't matter as much as the fact that the spatial designs were really biased and were giving a big downward bias. And so in the ETA metric, the time interval-based approach actually wins, right? And so basically the takeaway from this is that ETA suffers from this interference effect, whereas rides doesn't suffer as much from the same interference effect, and therefore the spatial designs do just fine. But there are kind of two takeaways here. One is that the sort of design choice that would be optimal among these three depends on what metric you care about. And usually you care about a number of metrics, and so it's kind of hard to make that decision, even if you had these simulation results, as to which metric you care more about. The second thing is that even though the time interval approach seems kind of safest and mitigates this interference bias and seems to do reasonable things, as I said before, it's very non-trivial to estimate variance for that type of design. And so you may not even know how well your experiment has performed, even if you chose this design. OK, so to sort of wrap up, I thought I'd give some ideas towards a way to get out of this conundrum using some of the literature that I mentioned earlier. So there's this paper I cited by Hudgens and Halloran. They do a very causal inference based approach to this, where they try to essentially decompose the total experimental effect that you're trying to estimate into a pair of terms, one which they call a direct effect and one which they call an indirect effect. And if you take the sum of those, you'll end up with the total effect, which is essentially the average treatment effect you're trying to estimate. So there's some math here. It's not super important. I think what's more interesting is the way that I chose to design this simulation, and that is as follows, with sort of what they call a two-stage randomization. So essentially, I did a hybrid approach between the interval and spatial designs, where I first, in each time interval, I randomly drew a proportion, a treatment proportion P, according to like just a uniform 0, 1 thing. And then I randomized that proportion of the spatial units to the treatment. So in every hour, that's going to be a different proportion of units. Sometimes like 90% of the spatial units got the treatment. Sometimes 90% got the control, and everything in between. And so then you can measure or try to estimate these direct and indirect effects. Just to give you some intuition, the direct effect is essentially what you would estimate for any given, it's a function of the treatment proportion here, but for any given design, you can say, OK, what was the difference between the treatment units and the control units within that design? That gives you the direct effect. That's sort of the naive and like most obvious thing you would measure. On the other hand, an indirect effect asks the question, OK, if I had two slightly different designs, so here they're indexed by P and Q, just two different randomization proportions, how would a control unit look different in those two designs? So comparing control to control, but in two separate designs, how would that unit's outcomes or potential outcomes differ? And so if there's no interference, you can imagine that that's going to be 0. And in most A/B tests, that's just assumed to be 0. OK, and so then there's some theory that says you can, and it's really just simple arithmetic, that says you can add these things up, take some limits, assuming some continuity, and get an estimate of the total causal effect. OK, so these are basically the last slide. I tried this out in a simulation just to sort of see how well it worked. So these points represent basically in bins of 0.1 treatment proportion on the x-axis what my estimates of the indirect and direct effects for this treatment, this subsidized prime time treatment would be. And so this is now in absolute scale. So the y-axis is in seconds of ETA. I'm focused on the ETA metric because that's the one where we had this interference problem. So these are the points I get. I fit some quasi-principled curves to these things and got something like this, which may or may not be a little bit judicious, but we'll see. For reference, the purple horizontal line is actually the true ground truth effect that we're after based on doing the full treatment and full control. So that's sort of the thing that we're trying to estimate. And these broken purple lines are what you get for the purely time interval experiment. So if you do no spatial randomization, just the time interval, as we saw, there were 2 clusters. So these 2 broken lines correspond to those 2 clusters. So you can see they're quite far from the ground truth, but on average they're right. It's just that you'll never observe the average. You'll observe one or the other, and you have exactly 50% chance of observing each one. OK, so basically the causal effects analysis says, easy, just add up the green the green curve and the orange curve, and as the limit approaches 1, you'll get your answer. So if you do that here, you actually get something quite close to the treatment effect you're after. So it's just the final point right there. And so it actually worked kind of remarkably well in this example. Now, there are tons of caveats. As I said, the curve fitting was somewhat judicious as well. I probably have more data here than is realistic in some scenarios, so maybe the true picture is a bit noisier. But I think the main takeaway I wanted to have here is that by thinking a little bit more cleverly and using some causal effects literature that's actually fairly old, we can potentially make progress on this problem and come up with experiments that are more efficient, for which we can efficiently and successfully estimate the variance, and for which we can have a good idea of what the true causal effect of interest is. So I'm gonna end it there. I have no fancy concluding slide or anything.